A linear differential equation is a differential equation that is defined by a linear polynomial in the unknown function and its derivative. And that is the equation of the form a function times y plus another function times y prime plus another function times y double prime, and so on, equals 0. Each of these functions, a sub naught x, a sub n x, and b sub x, and they are differentiable functions, and they don't have to be linear. The terms y prime, y double prime, y to the n derivative, they're all successive derivatives of an unknown function y with the variable x. For example, y prime of x plus y double prime equal to 0 is a linear differential equation because we can express this as some function 1 over x times y prime plus another function which is 1 times y double prime equals 0. Or xy prime plus y equal to 0, we can express this as the function x times y prime plus another function 1 times y equals 0. But y prime plus y double prime equal to 0 is not a linear differential equation because we have a function times y prime, but this function is not in terms of x, so this is not linear. Show that y times dy dx minus x equals 0 is separable but not linear. Then find the solution and plot the family of solutions. This differential equation is not linear because it is expressed in the form y times y prime minus x equals 0. So the equation that we use to multiply y prime, it is y, so it is not in terms of x, not linear. However, we can separate the variables y on the left hand side, x on the right hand side, as y times y prime equals x, or y prime equals 1 over y times x. And so it is a product of two functions. One is in terms of y only, and the other one is in terms of x. And so it is separable. So we can write this as dy over dx equals 1 over y times x, or y dy equals x dx. And then we integrate both sides of this equation to get the antiderivative of y is 1/2 y squared, and the antiderivative of x is 1/2 x squared. Now technically there's a plus c on the left and the plus c on the right, but we can combine the two coefficient constants to form one constant only. And then we still have to isolate y. Now y squared equals x squared plus 2c, so y equals plus or minus the square root of x squared plus 2c. This is the general solution. We see that when c is 0, then y is plus or minus the square root of x squared, which is plus or minus x. As c varies, we will end up with many different curves. Recall that a differential equation together with initial condition is called the initial value problem, IVP. So for example, given the differential equation dw over d theta equals theta w squared sine theta squared, and the initial value when theta is 0, w is 1, this is called the initial value problem, or IVP. We're going to use separable equation to solve w, and we're going to use the initial condition to find the particular solution. We move all the expression with w in it to the left hand side and all of the expressions that had theta on the right hand side. And then we integrate both sides of the equation with respect to corresponding variable. On the left hand side, it is the antiderivative with respect to w, and so it is minus 1 over w. And the right hand side, to find the antiderivative of theta sine theta squared, we can use u substitution, but we can guess that the antiderivative of theta sine theta squared is minus cosine of theta squared divided by 2. Note that if I take the derivative of minus 1 over w, I would have negative 1 w to the negative 2, which is good. And if I were to take the derivative of negative 1/2 cosine of theta squared, I would get negative 1/2 times negative sine of theta squared times 2 theta. Theta stays, 2 cancel out the 2, which is good. We still need to add a c. The question doesn't ask for a general solution. Given the initial condition, we're going to use this initial condition to isolate w to obtain a particular solution. Minus 1 over w, but w is 1, equals negative 1/2 cosine, but theta is 0, plus c. And that is, when theta is 0, w is 1. We then simplify this to get negative 1 equals negative 1/2 plus c, so c is minus 1/2. Minus 1 over w is minus 1/2 cosine of theta squared plus c, but c is minus 1/2. Negative 1 over w equals minus 1 cosine theta squared minus 1 over 2. We can get rid of the negative to get 1 over w equals cosine of theta squared plus 1 over 2. And then we flip both fractions to get w equals 2 over 1 plus cosine of theta squared. And this is the particular solution to this IVP problem.